As I mentioned in the last section, we're going to be using masses to compare what we might want to in a lab. I will say I don't particularly love this example because usually we're interested in the seam of a weld, and a lot of times acetylene oxygen mixture is used for cutting metal, and so although yes, we can compare them, and yes, there is a reaction equation there, I really don't like that example there. So this slide there, really wordy about just explaining what their new ratio here is, and really we've done this already. We've done moles over moles in the prior section. What they're pointing out here is we can turn grams of one substance into the moles of that substance, but now we have this new ratio here, moles over moles, that allows us to go from that substance to another one. Now, they didn't combine this with the flowchart from previously, so I'm going to take a little bit of space here, and if you're following along with the original printouts, this one is not there. But previously, we've seen that we can take moles of a substance, and we can turn it into the number of pieces of that substance. And if the number of pieces was a compound and not individual atoms, we could also then turn that into individual atoms. And we could also do the reverse process there. I've been drawing the double-headed arrows the whole time here. And we could also turn these into grams, or mass of the substance. Well, to do this one here, we needed the molar mass from the periodic table. For this one here, we needed Avogadro's number. And for this one here, if it wasn't atoms here already, we needed the chemical formula. Well, now, what this new ratio that we have that they pointed out at the bottom of the prior slide, that is this one here, I'm going to draw it instead of going across up and down here. And so this one here is how we go from moles of A to moles of B, and this is what I'm going to call the stoichiometry step. Well, once we've done that, we have moles of another substance, like moles of B, and we can go through all of those same conversions to grams of B, to pieces of B, and if necessary to atoms of B. Now, we won't do that very often. We did a lot of practice over doing Avogadro's number kind of calculations, and this part here isn't super useful. We mentioned, and we do these calculations previously, to emphasize that moles is how we can compare chemicals, and it can be a stand-in for other ways that we can measure them, other things that we can measure in the lab. And so in this section, we're going to look at this path here predominantly, where we can go from grams of one substance to grams of another substance, or vice versa, through our stoichiometry step. But if asked, you could go through those others, because this is just dimensional analysis. You know those units, and you know how to convert from one unit to another. So with that, let's try one of these. Suppose we want to determine the mass in grams of NH3 that can be produced. When I'm given a reaction equation like this, I like to put the quantities that I'm given right there with the reaction equation, from 32 grams of nitrogen. Now, something that we'll get to later on is we're assuming we have more than enough of this, that we're not going to run out of that. A lot of times that's called the excess, and I'll abbreviate that just excess reactant. So we're only given one quantity in the problem, so that we're going to start there. And previously, you may have gotten into the bad habit of dropping your units. You shouldn't, because we need them for dimensional analysis, but I've also mentioned that you should consider the chemical formula as part of your units. Now that is absolutely essential that you do. Anyway, we know that we can turn grams of nitrogen into moles of nitrogen. That's going to be the molar mass. I'm actually going to set up the framework for this one, and then plug in numbers. Here is our new stoichiometry step. We're given moles of nitrogen, and we want to get it into moles of NH3. And then lastly, since we're asked for mass of NH3, we need to go back from moles of NH3 to grams of NH3. these molar mass calculations here and here you've done before. And so the new step is really just this process of getting from moles of one to moles of another. Anyway, plugging in the numbers here, we know that the number that goes with moles is always 1 when it's above or below something else. The grams of nitrogen, it's 14.0 on the periodic table times 2. That's going to give us 28. Feel free to not do that math separately. The molar mass of ammonia here is 14 for the nitrogen times one of them, plus 1.01 times 3 for the hydrogen. That will end up being 17.01 grams there. And then, as I've pointed out before, our new step is the stoichiometry step here. And so we have an invisible one with the nitrogen. So, like I mentioned in the last section, when we have moles over moles, it can be something other than 1, but it doesn't have to be. But it's the only time we can have something that's not 1. You can see the 2 here on the ammonia there, and then we have our problem set up. It's always useful to go back through and check and make sure that your units do cancel, but grams of nitrogen will cancel with grams of nitrogen, moles of nitrogen with moles of nitrogen, moles of NH3 with moles of NH3, and you're left with grams of NH3. At this point, you just punch it into a calculator, and you're going to be left with 39 grams of NH3 when you round with sig figs. On this next one here, I'm going to do a little bit less color coding, especially because it's a multiple choice question here, but we're asked how many grams of O2 are needed to make 45.8 grams of the iron 3 oxide. So start with 45.8 grams of Fe2O3. We've done grams to moles before, but grams of Fe2O3. I suppose I should clarify, we know we want moles here because we're wanting to go from one chemical to another, and the only way we can do that is a stoichiometry step, moles over moles. And I've mentioned before, anytime you have grams, you should just think to yourself, I need to get that into moles of Fe2O3. The number that goes with moles is 1. For the mass here, I'm going to need to find the molar mass of iron oxide, so the iron is 55.85, and there are 2 of them, plus 16 times 3 of them, and that is grams. That's going to give me 159.7 grams. Then we know that we can turn moles of one substance into moles of another substance, and that there is our stoichiometry step. And so we have 2 moles of iron oxide here and 3 moles of oxygen there. And then lastly, we can turn moles of oxygen, since the question asked for a mass of oxygen. If it asked for moles, we're done, but it asked for a mass, so mass of oxygen, so it's going to be grams of O2, and that's just 16 for each oxygen times 2 of them, and there is our setup. Should always double check that our units cancel out, and so here we can see grams of iron oxide cancel with grams of iron oxide, moles of iron oxide with moles of iron oxide, moles of oxygen with moles of oxygen. We're left with grams of oxygen. And as a side note, anytime that you're given a mass, it is almost always 3 conversion factors for these kinds of problems. It's just a quick check. I don't like to memorize things like that myself because it's not always the case, especially if you're asked to solve for, say, just moles of that one, or you're given moles for starters but asked to go all the way to grams for the other. Anyway, this one comes out to be 13.8 grams of O2 when we round with sig figs, so that's going to be B there. So here we're told we made 13.1 grams of water, and the question is how many grams of O2 were used to do that. We're not worrying about the hydrogen there, so we start with 13.1 grams of H2O. Turn grams into moles, because anytime you have grams, you should get it into moles. Number that goes with moles is always 1. Now we're ready for our stoichiometry step, because we're going from moles of one chemical, water, into moles of another chemical, oxygen. And then we can turn moles of oxygen into grams of oxygen. That's going to be the same as the last slide. It was 16 times 2, so that's going to be 32 grams there. We know 1 is the number that goes with moles anytime we have it. 1.01 times 2 for the hydrogen, plus 16 times 1 for the oxygen gives us 18.02 grams for the water there. And then the last one here is our stoichiometry step, And so 2 moles of hydrogen to every invisible 1 mole of oxygen there. And now we're ready to plug that in to a calculator. I suppose I should double check that my units cancel out. Grams with grams, moles with moles, moles of O2 with moles of O2, and yes, they do. And so 1.6 grams of O2. I forgot I had added this in here, but previously we've seen this one based off of whether you're given individual elements or some kind of substance that has a chemical formula, and they have this flowchart that they had given you. And here we have moles of substance A, and pretend this is the different color here, and we have moles of substance B. And so just like I mentioned, we can go with a stoichiometry step from moles of one to moles of another. And so this one here is our new ratio. You can consider using the flowchart. You can consider putting it on your note card that you're allowed if you'd like. Personally, I don't like to do that because we're going to keep adding to it, and I think just canceling out your units helps, and I really don't like that they did this one as 2. As I mentioned previously, I kind of think of this one here as this, and then if this is an individual atom instead of a compound, we're done, and then we have that last ratio to get it from using the formula to get to individual atoms. I mentioned previously, I don't like to think of this as 2 separate processes, but either way, you can consider it. I like the one that I drew out by hand a little bit ago. I just know that this is a little bit easier to read, and the only new thing here is we can use the mole ratio of the 2 of them from the reaction equation to relate the two to one another. Anyway, that finishes section 8 here.